A grammar lesson. Yes, I know we're not in English class, but the idea is the same. A sentence has two parts, a subject and a predicate. The predicate is a verb phrase. So if I think of a mathematical sentence, I want to be able to say the same thing. There's a mathematical sentence. What's the subject of that sentence? The sentence is about what? About X. And the descriptor, the verb is, right? X is less than 5. So if I think of this as the subject, then the predicate can be thought of as something that applies to a given subject. So let's denote this idea as a sentence about X. That's a function, right? So I can think of the sentence as a function of the subject. I will define, this is an assignment symbol in a number of programming languages, that's why I'm using it here. I assign to the idea P of X the sentence X is less than 5. And then my truth value depends on what I plug in for X. So P of 2 is a true sentence. 2 is less than 5. P of 5 is false, because 5 isn't less than 5. It's less than or equal to, but I didn't say that. So now I have truth values based on my assignment of the variable X. By the way, in algebra, this is exactly what you do to create a graph, don't you? You plug in a value, and if it's true, you put a dot the right spot. So really, I can now shade the number line and highlight all the things where this is true. And if I do that, I'd shade in all those numbers, right? I remember this. This is a truth set for the relationship X is less than 5. That's what a graph is. Any statement involving a number of propositional variables can be thought of as a propositional function or a predicate function. If we think about the number of variables, well, then we can think about a unary function, operates on one variable. A binary function operates on two. This would be an n-ary function. Because it takes in n things. A lot of our programming language is designed based around this. Following I believe is a valid line in C, but my programming days were in a year that started 198. So it's been a long time since I've done any real coding. What does this do? Oh, it checks whether this function is true or false and does this operation if it's true. If it's false, it doesn't. but there's my predicate function to start with. Now, if I am looking at this piece of code as it operates, I can look at it before we act and after we act. These are called preconditions and postconditions. And the way in which we check the value of our variable depends on where we are in the sentence. There's an example on page 43, example 7, which switches the values of x and y. So the first thing it does is it pushes whatever the value is from x into the thing named temp. Then it takes whatever the value is in y, puts it in x, takes whatever we put in the spare pocket temp, puts it back in y. So what was in x is now in y, and what was in y is now in x. But we had to have this spare place to put something to do it. I want to verify this. When I run a debugger, it will show me line by line by line what's in what thing. As I go through each step, here's where I started before I did the instruction. Here's where I am after the first instruction, after the second instruction and third instruction. It's a good way to make sure this is doing what we think it should be. Okay. One of the things we do when dealing with propositional functions is to figure out how many cases this will have where it's true. How many cases will it have where it's false? I might want to know something about how many. A quantifier is a way of counting. The root word is quantity, right? So I want to know how many. There are two commonly used quantifiers in formal logic. The first one is called the universal quantifier. So I have this idea of a propositional function p of x. And I want to say that it's true universally. All right, wait a minute. What does that mean? Universally true.
Always true.
Always true. So that capital upside down letter A is read for all. For every value of x that's possible, p of x will be true. Now you'll notice I didn't actually write is true up there. The assumption is that we are stating a true thing. So for all x, p of x means I want p of x to be true. You can also write for every, for each, as long as we're talking about the domain of x. So if I'm talking about something that works for numbers, I might have to specify what kind of numbers it works for. Work for even numbers, integers, rational numbers, irrational numbers, real numbers, complex numbers. I have to specify my domain. I could not be talking about numbers. I could be talking about people. If I'm talking about people, what group of people am I asking about? For example, I could be talking about students. Am I talking about students in a particular major? I'm talking about students in a particular class. I'm talking about a certain year of students. So I need to make sure I specify the domain of x somewhere. Notice if the domain is finite. This is really an and statement. If the domain of x is finite, well, that means x1, x2, all the way up to however many there are, right? And what I've said up there is for all x, P of x is true. That's the same as saying it's true for x1, and it's true for x2, and it's true for x3, and x, aha. Then we're really doing a giant and statement. Now, there are a lot of places where I use a finite set of numbers. We'll get to some of the places where these things are. There's this thing called modular arithmetic. Anybody of you used or heard of modular arithmetic so far? Okay, a couple of you, but not many. The idea is that I take a number and then I divide and I look at the remainder. So let's consider dividing by 3. If I'm looking at the numbers when I divide by 3, then there are only 3 possible remainders, 0, 1, and 2. Here's an interesting statement. Let me call this set S. That symbol means X is a member of S. We'll also use the phrase an element of S. I claim this is true. This is a universally quantified statement. I claim for every one of those numbers, if you square it, you either get a 0 or a 1. But I can actually physically check, can't I? What's 0 squared? That was easy. What's 1 squared? What's 2 squared? Wait a minute. I have to divide by 3 and take the remainder. What's 4 divided by 3? 1 and 1/3. The remainder is 1. It works. But I could literally go through and check every individual case. Last time I checked, this is a true statement. What would make that not a true statement? By the way, there are different domains where this statement is false. I hope you can look at yourself. I am a person. I'm in this domain. I have 2 biological parents. 2 different people contributed to me genetically to make me a person. Yes? So what would make this false? If I change the domain. So sheep. I need you to look up your computer in front of you, Dolly the sheep. Use your phone, Dolly the sheep. Tell me what's interesting about Dolly the sheep. Let people look. Dolly the sheep is a clone, has one biological parent. Even if I stay in this domain, we may get to the point where we can clone human beings. And then that person will have one biological parent. We are looking at curing certain inheritable diseases by grafting genetic material from one person to another. Dr. Steve Bassett, who used to be on the biology faculty here, worked for an organization researching mitochondrial diseases. And it is possible to take mitochondria from a healthy person, transfer it into an unhealthy person, and have that person's genetic material altered. You can do this in utero, which means I can do it to you before you are born. And then you would have 3 parents, not 2, because you have genetic material from 3 people. Go watch the movie Gattaca. Science fiction movie, Ethan Hawke. It's a bad movie. But the idea is that you live in a society that does genetic editing before children are born. If I can do that, this will no longer be true. I can have as many parents as I want. Take this from this person and this from this person, and I build myself a chimera. Now, the idea that the domain matters even can be worked with just in numerical statements. Depending on my domain, this sentence could be true or it could be false. Let's assume our domain is integers. Somebody tell me, what is the set of integers? I promise we'll talk about sets and all sorts of different sets of numbers a little bit later on, but this one I can look up at the moment. What are the set of integers? There's a lot more in there, and there's a little bit of a restriction on what's in there. So yes, and they're going to go from minus infinity to infinity, but
Just like the parentheses or
that's whether I've got the endpoints of a set included. Square brackets include them, round ones don't. They have to be whole numbers. So -2, -5, -13, 73, 102, 0, no decimals, no fractions, nothing in between. Just positive integers, negative integers, and 0. So whole numbers on the negative side, whole numbers on the positive side, and 0 itself. What's 0 squared? Makes that true, right? 1 squared. -1 squared. Matter of fact, when you square a negative, what happens? So they're all bigger, right? If x is negative, I'm always going to make this work. 0 squared is 0, 1 squared is 1, 2 squared is... And they keep getting bigger as I go that way, right? Did we ever get one that was smaller? Not if I'm dealing in integers. In integers, this is a true statement. As a matter of fact, if I think algebraically, I draw the graph of x squared, I draw the graph of x. This is 0 right here. This is 1 right here. And once I get to 2, well, this graph is clearly on top, isn't it? And all here over the negative side, this graph is always on the bottom. So this is definitely going to work. And I've actually listed all the possible cases we could have. Technically, I have examined all the options. I'm good to go. But it really is only talking about the dots. Like that, right? Notice what happens between 0 and 1. If the domain is all real numbers, then I could use a fraction, couldn't I? What's 1/2 squared? And in that case, x squared is smaller than x. So my choice of domain influences whether my universally quantified statement is true or false. Please notice, and this is an important idea, as soon as I find one example of it being false, the universally quantified statement is false. In other words, it takes one bad apple to spoil that bunch. A single counter example. The issue, though, is we actually have to find that counterexample. And that's not always easy. Questions? I did say there were two quantifiers that I like to use a lot. The other one is called the existential quantifier. The symbol for the existential quantifier is a backwards capital E. The universal was an upside down capital A for all. This is a backwards E for exists. Existential, right? So, how would I read this sentence? I'm saying something exists. I want P of X to be true. What this says is there is such a thing. Somewhere out there, there's one that exists that you can find and put it in, and it works. I'm going to read it exactly that way. There exists. But it just says there's some. There's one. There might be more, but there's one. And that's the advantage of this. Says there's either one or more. There might be 73 of them. There might only be 6 of them. There might only be one of them. But there's one at least. It could be a lot more. As a matter of fact, a sentence like this has infinitely many places where it is true in the set of real numbers, for example. So, Evan, I'll set this up the way you want it to, on minus infinity to infinity, right? Yeah, 3, 4, 5, 6, 2.8, 2.8 doesn't work. 5.8 works, right? But there are a lot of them. On the other hand, I would like you to tell me what number satisfies this equation. I like that face, Gracie. What number is equal to itself plus 1? There ain't no such thing. So if I'm using these two propositional phrases, I can say this: there exists x, p of x. That's true. There exists x, q of x is false. I can't ever find one that's going to work that way. Hey, wait a minute. The universal quantifier was a giant and. When I have a finite collection of things, I can go through and check each and every one, and they all have to work. What's an existential quantifier going to look like? A giant or. At least one of them has to be true, and then the or statement will be true. Now, I don't often use the following expression, but we can modify this ever so slightly. It is possible that I don't want to just say there is some. I want to say there's one and there's only one. And that gets done so frequently in math that we actually write this. There exists, and then an exclamation point, x. This means there's exactly one. But really what that means is two statements. It means something like this. There exists an x where p of x is true, and for any other value, for any y not equal to x implies not p of y. Now that actually looks much more complicated, doesn't it? Hey, it's true for something, but if you pick anything else, it's false. That means it's only true once, the special value of x that we found at the beginning. This is much shorter. So you'll see that in a lot of logic books and a lot of places where we do decide on how we're going to write this setup. It's worthwhile remembering. You will be asked to take things that look like this and write them like this so we can understand a better way of what that uniqueness means. Please notice this puts one quantifier after another. That's a little more complicated. So keep this in your back pocket for the moment. We'll talk more about it next week. Questions? These are getting used in my logical statements, right? I need to put them in my order of operations. Where do they go? They go before everything else. If I'm talking about something about y, I need to know what quantifier applies to y before I do anything. So these take precedence before everything else. I used to have not at the very top. These go above those. They have highest precedence in making all of the other operations we've done so far. Questions? I can have a propositional function that has lots of different variables in it, right? My quantifier might only apply to some of those variables. I don't know what the function q of xy is, but it clearly involves two variables. My quantifier, on the other hand, is only talking about x. So in this statement, x is called a bound variable. It is bound to the quantifier. That variable is in the scope of the quantifier. On the other hand, this doesn't tell me squat about y, right? Y could be anything. It's not, it might be something fixed. Maybe I'm going to talk about people. My domain is people. Q of xy means x likes y. If I wrote Q for all x, Q x Jimmy, then everybody likes Jimmy, right? But Jimmy's a free variable in this. The quantifier doesn't apply, even though Jimmy could be x as well. Jimmy likes himself. So this scope tells me what is bound. Variables that are not bound are called free variables or unbound variables. Now, being bound is the same as being outside the scope. of the quantifier. X is in the scope, it's bound. Y is out of the scope, it's free. When I am working with multiple propositions, multiple variables, I can have multiple quantifiers in the same sentence. Now, the way this sentence is written makes me a little twitchy, but let's think about the existential quantifier over here on the left. There exists an X, P of X and Q of X are true. That means somewhere along the line, I can find an X and it'll be true, P will be true, Q will be true for that value, that person, that object. Or for every X, R of X is true. The X I'm using over here, this X, this quantifier, its scope is only those two pieces. The variable X is bound to this quantifier and used here. This X is bound to this quantifier. If I were writing this for myself, I would prefer to write it like that. But those two sentences say exactly the same freaking thing. I don't care what letter or symbol you are using for your variable, as long as it's in the same domain. The scopes of the quantifiers don't overlap here. They're separated by that logical operation in the middle. Questions? What would it take for this sentence to be false? I asked that in the universal quantifier statement. Now let's ask it here. What would it take for this quantified statement to be wrong? Well, this just says there is such a thing, right? It doesn't say there's only one thing. The exclamation point would be only one thing. So nothing. Aha. It's never true. Hey, wait a minute. Let me think about this for a second. A universally quantified statement gets blown up if I find one where it's broken. An existentially quantified statement gets blown up if it's always broken. The negation of an existentially quantified statement is a universal statement. It doesn't work everywhere. The reverse is true. The negation of a universally quantified statement is an existential statement. The opposite of it always works is it breaks at least once. At the bottom of page 44, we talk about when a quantified statement is true versus when it's false. And at the bottom, top of page 51, we have the negation of our quantified statement, which is really the idea of De Morgan's law, isn't it? The universal was an and, right? And when I take the negation from outside an and to inside it, I change it to an or, and the existential is an or. It flipped. It works the same freaking way. A universally quantified statement. This is a universally quantified statement. The domain is you. Every student in this class has had me as a teacher before this semester. What is the negation of this statement in English? I think it helps to translate it to symbols, do the negation there, and translate that into English. So I need a propositional function to describe the predicate of this sentence. What is the predicate of this sentence? So I'm going to use P of X. X has had me as a teacher before this semester. That's my definition of the function I'm going to use. Sure, I want that there. Then my sentence up here in quotes should be written as, for all x, P of x, where the domain of that function is students in this class. Great. The negation of a universally quantified statement. Right there. The negation of my universally quantified statement is an existential statement. I take the not from the outside to the inside. I flip the universal and to an existential or. Now, what is that in words?
At least one student in this class has not had a teacher replacement.
There you go. At least one student in this class has not had me as a teacher before this semester. The negation now applies to this. Now, maybe I want this domain to apply to all students at Seton Hill. Then somehow I should add being in this class, right, to my description. So maybe I could say we'll add another propositional variable or predicate function. C of x is a student in this class. And then I could say for all x, C of x and P of x. Then the negation would be there's a student not C of x and P of x. Well, that not becomes an or, doesn't it? So they're either not in this class or they haven't had me before. When I'm dealing with a single quantifier, swapping back and forth between English and geek speak, I think is pretty straightforward. Using the negations becomes a little more complicated. By the way, that also means I need to be able to negate all of the other operations we've had. This is where I go back to those tables. What was that, page 27 or something? With all those logical equivalence things on them. If I want the negation of an if-then is only false when the first part is false, and the second part, sorry, where the first part is true and the second part is false. I want that to be the only true. So the opposite of a negation, sorry, the opposite of an implication doesn't have an arrow anymore. If you study, then you will get good grades. The only way that's a lie is if I study and I don't get good grades. They have the exact opposite meaning. I have to be able to move that negation in there. I will tell you up front, one of my favorite books in the world is a logic book. Charles Ludwig Dodgson wrote an amazing set of books to teach logic to his niece. He didn't publish them under his own name. He published them under a pen name, Lewis Carroll. His niece's name was Alice. Alice in Wonderland is a logic book. The Cheshire Cat, the cat that grins and then turns invisible and all that's left behind is the grin. I've seen a cat without a grin before, but I've never seen a grin without a cat. That's a converse statement. The entire book teaches logic. Go watch Alice in Wonderland. You'll be astonished at what you see now. I want to do more on quantifiers on Monday. I want to look at the way one quantifier goes inside the scope of another. So this idea back here, where we had one quantifier with another, I want to look at that again more closely on Monday. I will see you all then. Have a wonderful weekend. Enjoy. If you came in late and I still have your work, come get it. Otherwise, I'll see you then.